Okay, so our last common section that we have is hyperbolas. So if you take a look at the chart here, so if you remember for hyperbolas, looks a lot like an ellipse except subtraction in the middle. In this case for hyperbolas, C is your biggest value, so it doesn't matter if A or B is bigger. The way that you're going to tell for A is going to be with the positive one. So for here, A was under the X and X was positive. So this means it's going to open to the left or right. Whereas here the positive one was Y, so A is under Y, making the hyperbola go up or down. So if you take a look at the parametric equations, they look a little different than the circles and ellipses did. So they have secant and they have tangent. So the Pythagorean identity that you're going to use for hyperbolas is secant squared t minus tangent squared t equals 1. Okay, now this has subtraction in the middle, and so you're going to make sure you line it up with the hyperbolas. Subtraction lines up with the correct hyperbola, and then you have your secant squared and tangent squared. We'll kind of talk about the graphs and stuff as we get to that problem. So for this first problem, it is in rectangular form. We know that this is a hyperbola because it has subtraction. Okay, X is the one that is positive, which means that our hyperbola is going to open to the left and the right. And so our A value would come from the 16, the square root of 16. Okay, so underneath this, I'm going to write my Pythagorean identity we're going to use in secant squared minus tangent squared t is equal to 1. So it already has the equal to 1, which means we can go ahead and just compare. Okay. Once again, just like with the cosine squared plus sine squared, everything is squared. So if you want to go and take the square root in your first step, you can do that. So if I take the square root of the secant t, it's just going to be secant t. And then equal to the square root of x minus 2 squared will be x minus 2. Square root of 16 will be 4. So remember for parametric, the goal is to solve for your x equation and y equation. So if I solve this for x, I'm going to cross multiply. And then I'm going to add my 2 over and I'm going to put it out front. So I end up with x equals 2 plus 4 secant t. Do the same thing over here. I'm going to compare. Take the square root of all the parts. So we're going to end up with tangent t equals y plus 1 over 6. I want to solve for y, so I'm going to cross multiply. I'm going to subtract 1, and I'm going to bring that 1 out front. So for y, I end up with negative 1 plus 6 tangent t. So just to talk about this for a minute, these are the parametric forms. This is 4. This is 6. So we have secant, tangent. They should have different numbers because it's a hyperbola. Secant should always be your positive one. So in this case, because secant is always your positive, the A has to be 4, and so the B has to be 6. Remember, A does not have to be bigger for a hyperbola, it's just for an ellipse. So secant will always be your positive one, so your A value is always with the secant. Yes. And then for the center of your hyperbola, you can get it the same way we got for the circles and ellipses. So this is positive 2. And that's going to be negative 1 there. Okay, so looking at the next one, we're going to go from parametric to rectangular. So they give us 2 tangent t and y equals negative 2 plus 3 secant t. Okay, we know just from looking at this that this is going to be a hyperbola because we have the tangent and the secant. Okay, so let's go ahead and write down the identity that we're going to have to use. So we know that secant squared t minus tangent squared t equals 1. This is the equation that we're going to be using. So we need to solve for tangent and we need to solve for secant. So I'm going to take the top equation and we're going to solve it for tangent. So the only thing you can really do is just divide by 2. So x over 2 is tangent t. So I'm going to go over here and plug this in. this is tangent squared t, so I need to make this x squared over 4. And then I'm going to take my other equation, solve it for secant. I'm going to add over my 2. And then we're going to divide by 3. So secant t is y plus 2 over 3. This is secant squared, so we're going to have to make it y plus 2 squared over 3 squared, which is 9. So that is going to be our rectangular form of our hyperbola. So things for this hyperbola. Let's talk about the center first. So my center, the x-coordinate of the center will be 0. The y-coordinate negative 2. So let's look back at our parametric equations because I forgot to do this at the beginning. X does not have a number out front, so there's 0, so that's good. Negative 2 out front, so we have that there. Y is the positive here. So because y is the one that's positive, that means your A is going to be the square root of 9, which is 3. And your B is going to be the square root of 4, which is 2. Remember I told you the one that's positive is always with the secant. So in this case, this time it's y here is 3 secant. So your A value is 3 and your B value is 2. Because the y is the positive one, so here and here positive, because y is positive, that means it's going to open up or down. So if we just sketch a little graph here. Okay, so we know that our center is 0, negative 2. Okay, so the A value, you can think about it the major axis. So for your A value, we're going to be moving up and down because that's y plus. So I'm going to go up 3 spaces. I'm going to go down 3 spaces. And then if you remember, the B value really has no, you're not going to graph those points for the hyperbola. So this is going to be going up and down. Now if you remember, we have those asymptotes that kind of help you figure out how wide your parabolas are going to be. So we can get the slopes of them. We always have 2. We always have a positive one and we have a negative one. And if you remember, slope is always rise over run. So think about y over x. So for this problem, since it's rise over run, y over x, you're going to use the y value, which is square root of minus 3, over the x value. So your asymptotes are going to have slopes of plus or minus 3 over 2. So we're going to start at our center. We're going to go up 3 spaces over 2 spaces and down 3 spaces over 2 spaces. Draw in your asymptote. Then you're going to go up 3 spaces to the left 2, down 3 spaces to the right 2. So there's your asymptotes. So that way when you draw your 2 parabolas in hyperbola, they can go really close to your asymptotes without touching. So there was your hyperbolas. And then on this last slide, we are just given a bunch of parametric equations, and we want to figure out if they are a line, parabola, circle, ellipse, or hyperbola without having to put them in rectangular form. Okay, so I really like this. I think it's really good practice. So looking at number 1. Number 1 has cosine and it has sine. So it's either going to be an ellipse or it's going to be a circle. So the way you're going to tell is you're going to look at the number in front. So because it says 4 cosine t and 4 sine t, now remember, it doesn't matter if this is positive or negative in front because that square root is the reason all that, and when you square it, it'll take care of it. But because it has the same number 4, that means this has to be a circle. So number 1, 4 cosine, 4 sine has to be a circle. So what I want to do next is I want you to be able to pick out of the ones, just glance, which one would be an ellipse. So if you remember, ellipse is very similar to a circle. It has cosine and sine, but different numbers out front. So if you take a look at number 6, we have this 2 cosine t and 3 sine t. So it has cosine and sine, but different numbers out front. This one is going to be an ellipse because of that. So back to number 2. If you look at number 2, there's no sine, cosine, secant, or tangent. So it's not going to be a circle, ellipse, or hyperbola. It's either going to be a line or it's going to be a parabola. So remember, lines just have x's and y's, whereas parabola, one of the terms is going to be squared. So keeping in mind, because this has this x, or this t squared here, this is going to make this be a parabola. Okay, so because of that t squared, if it didn't have that t squared, it would have been a line. Because of that t squared, it's going to be a parabola. So looking at number 3, there's no trig functions here, but we have just 2 minus t and 3t. So because these are just single t's here, this is going to be a line. Alright, number 4 has this 4 secant and a 3 tangent. So the only type of conic section that has secant and tangent are hyperbolas. So number 4 is going to be a hyperbola. And then number 5 is a little bit tricky. So it does not have a trig function. So it's either a line or a parabola. If you look at just the y, it just has a t, but then you have the square root of t. So because we have this square root of t, if you were to actually solve this out, if we were to divide by 2, and to get rid of the square root, you would have to square both sides. And now you have this x squared that's going to come in because of that square root. So that is why it's going to be a parabola. So that square root of t, whenever you were to solve that in rectangular, it would make it be a parabola and not a line. Okay, so those are parametric equations versus rectangular. Parametric is going to have 2 separate equations, one for x, one for y, and it's going to have an extra parameter. Might be t, might be theta. They might use a random letter there, but it's going to have some kind of extra parameter. Rectangular is the type of equations that you're used to, but parametric gives more specific, a way to look more specific, especially at a certain time. What is the x coordinate? What is the y coordinate?